Okay, Math 31s. I had a couple questions about the limits assignment, so I just wanted to go through some of the questions that I was informed people were struggling with. So the first one was number 9 in the lesson. And number 9 had the limit as x approaches 0 of sine of 7x over sine of 4x. Now remember, our goal is to get sine x over x or x over sine x. Now, if you had sine of 2x over 2x, it still equals 1. So as long as we balance what these two values are to make them the same, then we get a limit of 1. So that's what we're going to try to do with this one. So I'm going to split this up as the limit as x approaches 0 of sine of 7x. And then over here, I'm going to put sine of 4x. Now, I need to add some stuff to balance this expression out. So I know that I want to put a 7x here on the bottom, but I can't just magically add 7x to the equation or the expression. Add it on the bottom and on the top. So now I know that this 7x and this 7x actually cancel each other out. Now I'm going to do the same thing with my 4x. So because I have a 4x here, I want to add a 4x here. But I can't just add something on the top. I have to add it on the bottom. Now when we have these values, my limit as x approaches 0 can now be written as sine of 7x over 7x, 4x over sine of 4x, and then I'm just going to move this to the end, and what happens to my x's is they cancel, and I'm left with 7 over 4. Now when I take the limit, we've discussed that this equals 1. This equals 1, and this, the limit of any constant, is a constant. So my answer is just 7 over 4. Now I'm going to do another one from the homework that's quite challenging on page 306. The first one is number 7. And then I'll do number 9 as well. So number 7 says you have the limit as x approaches 0 of sine of 3x over x. Now, we know that this is 0 over 0, so we can't get that. So we want to go like this. We want to say, okay, well, I have the limit as x approaches 0 of sine of 3x. I want to balance this out. I want to make the denominator have a 3x. So I'm going to put a 3 and I'm going to put a 3 here. What happens is I move that 3 outside. I have the limit as x approaches 0 of sine of 3x over my 3x. I know the value of this is 1, and 3 times 1 is 3. And that's how I would do the question. It's way more complicated if you decide to use double angles and splitting up your x's. So we are not going to do that. Question 9. I have the limit as x approaches 0 of sine 2x, and remember this whole thing is cubed, over sine of 3x, and this whole thing is cubed. So we're going to do what we did before, and we can rewrite this. Keep this in mind. Okay, so I have the limit as x approaches 0. If I'm dealing with sine of 2x, that's sine of 2x times sine of 2x. The same thing. Now, if I wanted to add a 2x on the bottom, a 2x on the bottom, and a 2x on the bottom, what would I have to add to the top to cancel out those 3 2x's? That would be 2x cubed, or 8x cubed, which is the same as the bottom. Now, for the denominator, I have sine 3x, sine 3x, sine 3x. What do I want to add to the top of all of those so that all of those limits equal 1? I need to add 3x, 3x, 3x. But what cancels out those 3x's? 3x cubed. So now that I've balanced out the numerator and the denominator with this guy right here, I can evaluate all of these limits. This is 1, this is 1, this is 1. This one becomes 8 over 27. My x cubes are going to cancel. I'll write those in, but they cancel. Times 1, 1, and 1. So what do I end up getting? 8 over 27. So all we're doing is balancing out the equation. What you add to the bottom, which was all these 2x's, you add to the top. So I'll do a couple more from the homework. Number 17, you have the limit as x approaches 0 of tan of 3x over 3 tan of 2x. Now, if I plug in my values, I get 0 over 0. We always want to plug it in and see what happens. So here what I'm going to do is I'm going to split the limit, and I'm going to rewrite tan. I'm going to write that as sine of 3x over cos of 3x, divided by, and I'm going to do the same to the bottom, 3 sine of 2x over cos of 2x. I'm going to reciprocate and multiply. I get sine of 3x over cos of 3x times cos of 2x over 3 sine of 2x. Now, this is where the balancing part comes into play. Okay, I'm going to split up my functions. So what I'm actually going to do is write this cos over top of each other. Right, so I could write this as cos of 2x over cos of 3x, and I could write the sine of 3x over 3 sine of 2x. So I'm just rewriting it. Now there's no issue with our coses at 0, like we're going to get 1 over 1. So this doesn't need to be balanced. This is just going to be 1 over 1, which is 1. But this guy, we have to do what we did in the last two examples and balance it out. So I'll split this into my limits. So I have my limit as x approaches 0 of cos of 2x over cos of 3x times my limit as x approaches 0 of my sine of 3x over my 3 sine of 2x. Now, to balance this one, we're going to write this as the limit as x approaches 0 of sine of 3x over something. And then I have my 3 sine of 2x over something. So I'm splitting it up. And here's where I'm going to balance it. What do I want to add to the bottom? I want to add a 3x. What I add to the bottom, I add to the top. What do I want to add over here? I want to add a 2x. I want to add this angle. And what I add to the top, I add to the bottom. Now it's balanced. Now what is the limit of this? 1. What is the limit of this? 1 over 3. What is the limit of this? 3 over 2. And then the limit of this one is 1. We multiply all of our values together, we get 1/2. So you can split them up. When you have a tan or a cosecant or a secant, you want to replace them, just like we did in our proofs in 30-1, with sine or cosine. Couple more. So that was number 17. Let me show you some of the harder ones, like 31. So you have the limit as x approaches 0 of sine squared x cos x over 1 minus cos x, which is 0 over 0. So what I'm going to do is I'm going to rewrite Pythagorean identity 1 minus cos squared x, cos of x, over my 1 minus cos of x. When I factor, I get 1 plus cos x, I get 1 minus cos x times cos x all over 1 minus cos x. What happens to my 1 minus cos x's is they cancel. I am left with cos x times 1 plus cos x, which when I plug in my zeros, I get 1 times 1 plus 1, which is 2. You can also use the conjugate for that one as well, and you get the same answer. Okay, question 33. You have the limit as x approaches 0 of sine squared x cos x and 1 minus cos of x. What do you think we're going to do here? The same thing we did in the last example. Replace this with 1 minus cos squared x, cos of x, and 1 minus cos x. This time you're going to see what cancels. We factor. One plus cos x, 1 minus cos x, over 1 minus cos x. Actually, is that the same one as 31? I just did the same one. Sorry. It must have been plus, maybe. 33. Oh, it's the wrong one. Sorry, this is the same. This was just 31 again. Okay. The last thing that I want to clarify is your derivatives. Now, the derivative of sine of x with respect to x is cos of x. You just have to know that. And then the derivative of cos of x is not sine x. They're not just opposite, it's negative sine x. So I just want to go through the proof because I had a couple questions of why is it the opposite? Remember, it's not the opposite. This is a negative. So you have to keep in mind that the derivative of negative sine x is cos x. The derivative of cos x is sine x. So they're not exactly the same. So if f of x is equal to sine x, remember how we proved all of this stuff before? We used that fun little formula using our limit as h approaches 0 of f of x plus h minus f of x all over h. That's how we prove every single type of derivative, because that's the definition of it. That's how we started with it. So if I do this, and I write that f prime of x is now equal to the limit as x approaches 0 of sine x plus h minus sine of x all over h. You might remember that this is called a sum. And a sum of our trig functions goes like this: sine of x cos of h plus cos of x sine of h minus my sine of x. So that's just using our identity, sum, difference. And for some of your limits that you were struggling with, if you look in the solutions of the book, they use sum and difference to prove some of this stuff, and I can show that after as well. From here, what we're going to do is we are going to factor out of the first term our sine x. So I'm just going to bring together my sine x terms together. So I have a sine x cos h minus a sine x plus my cos x. So I'm just rewriting the numerator. And then out of here, I'm just going to factor out a sine x. I'm left with cos h minus 1 plus cos x sine of h all over h. Now, if you remember, I can split this up into two. I'm going to pull out this sine x and write it as a limit as x approaches 0. And then I have my cos of h minus 1 over h plus this cos of x and my limit as h approaches 0 of sine h over h. Because remember, cos, these are constants. These are just numbers. Okay? They don't have an h value. So those are numbers, so we can pull them out. They're constants. Or just a number. So our rules say that we can pull them out. But now we're evaluating stuff from 7.1. We know that this had a value of 1. So really we're saying sine at 0, or sorry, had a value of 0. And this one we said has a value of 1 for our limits. So what we're saying is we're going sine of x times 0 plus cos of x times 1. Well, this just becomes 0 plus cos of x, which is cos of x. And that is the value, or the proof, of how the derivative of sine x equals cos of x. And the proof for the second one is the same. So you guys will have a formula sheet where you will have all of the different derivatives. So to add to our list, we have the derivative of sine x, we have the derivative of cos x, we have the derivative of tan x, let's see what other ones I'll write down for you guys. So this one we have cos x, this one we have negative sine x, this one we have secant squared x, what other ones should we use? We have derivative of cosecant x, which is a weird one, negative cosecant x cotangent x. We have the derivative of secant x, which is secant x tan x. And another weird one, finally, the derivative of cotangent is negative cosecant squared x. So those are all of your trig derivatives that you will go through, that you need to know, and you have to just have them memorized. So in calculus, you will have those all memorized. I like to make cue cards, as I've told you before, to help you know all of those ones. Okay, so hopefully that was a little bit more clear. Always email me with any questions that you have.